Okay, so we need probability theory to develop sampling theory that then leads to inferential statistics, because what we've done so far is talked about descriptive statistics. And so we're going to take a pause on descriptive statistics and talk about theory, probability theory, build the theory, and then we're going to apply some of the theory. So that's going to be for modules 6 and 7, and then 8 and 9. No, sorry, 8. But then in 9, we're going to go to inference. And inference is really, all of this is, we're building up to talk about inferential statistics. It's a branch of statistics. It's in contrast to descriptive statistics, where you just show what you have. Like, this is what we have. But inferential statistics asks questions of what you've got, and you can hypothesize about the state of the world, certain variables or characteristics, and then you can test based on data using sampling theory. You can test whether in fact your hypothesis is accurate or not. Okay, so that's the goal of what we're doing. And so the first part is just reviewing statistics. I think a main point is this one. What is reviewing probability, or introducing and reviewing probability. And people have an idea of, again, a lot of this, people have an idea of terms, but what do we really mean? So what is probability? So I use the example of flipping a coin. A coin has two sides, a head and a tail. Usually you have the head of a past president on your coins on one side, and then on the other side we call that a tail. Whatever's there is an image or something that's been stamped on the coin. So when you flip the coin, you can expect to see the head just as many times as you expect to see the tail, if provided that you flip it enough times. So because we have a notion that it's a fair coin, then, and the idea that if we keep flipping this coin, out of the total number of flips, we should see a head 50% of the time and a tail 50% of the time. So this graph illustrates that experiment, or that phenomenon. If I was to flip the coin once, I'll just see a head or a tail, and I can mark that. This marks here proportion of heads. So out of 1, I saw a head, so that's 100%. Now I could do this again. I could do this. I can make a whole new chart, repeating it. It'll look a little bit different at the beginning, but the end, if I add more flips, if I flip twice, and here it's showing, I think this is 50%. So one was a head, one was a tail. If I flip twice, so that's 50%. And then, so we flip again. So the beginning will be a little different if I start this chart, but in the end, if I flip it enough times, it looks like by 1,000, pretty much 50% of the flips will be heads and 50% will be tails. So it takes a while to see, like it takes a number of trials to be able to exhibit that expectation, right? That you're going to have a 50% chance. So probability is really, by definition, long run relative frequency. So if someone says, look, I flipped this coin so many times and I keep getting ahead, something's wrong with the coin, or the person hasn't flipped the coin enough. And I give several, I illustrate several examples here, and you guys should go read through and watch the videos. Then I began talking about some of the terminology, and I introduced the idea of a random experiment. So not just flipping one coin, but flipping 4. And I'm going to define the variable X. So, until here in the notes, I use X for the normal distribution, right? But it's just a name, a label. I'm going to use it for different kinds of distributions. And here I'm going to call X the outcome of flipping 4 coins. Now, this is not a normally distributed variable. It's not a continuous variable either. What kind of variable is this?
Is it categorical? Categorical?
Okay, so yes, we put it in the category, we call it a discrete variable, right? So broadly speaking, it's a discrete variable, not continuous.
Oh yeah, because it's so like an objective.
Because
No?
well, continuous means that you can have fractions, remember? So
Yeah,
it's still quantitative, it's not categorical, it's quantitative, but it's not continuous, it's discrete, if you remember back to the second module.
oh yeah, because it's no decimals or nothing. It's like
Exactly.
okay, yeah.
So in the terminology we learned before, it's quantitative, but it's discrete, not continuous. And because it's discrete, I have a fixed number of outcomes as well, right? I can actually list them. And if I use this notation to say, okay, either it can be 4 heads or 3 heads and a tail at the end, or it can be 2 heads, a tail, and 3. So this is the way it can look, the appearance of the outcome. And I can make a list and I can put them all down on paper. So it's not continuous. Continuous outcomes are infinite, right? Infinite possibilities. So we call this set of possible outcomes the sample space. And in probability theory, so I review the rules of probability, and well, one of the rules is all probabilities have to be between 0 and 1. In an outcome, for a variable like this, this is the variable, these are the possible outcomes, and analogous to making a normal distribution and saying that under the curve is 100%, we say here all the possible outcomes, their probabilities sum to 1, okay, in the sample space. So since these must sum to 1, and since each one is equally likely, I know they're equally likely because on each flip, the chance of a head is 50%. On the subsequent flip, the chance of a head again is 50%. Or the tail, because I defined it. No, I just said outcome. Okay. So it's 50% each time. It doesn't change from flip to flip or trial. And so these are all equally likely. If they have to sum to 1 and they're 16 and they're equally likely, then each probability must be 1 over 16. And I explained that here. If there are n finite possible outcomes in the sample space and each is equally likely, then each individual outcome has a probability 1 over n, because 1 over n times n is 1, right? Because you're adding all the probabilities up. Or you could motivate that, I could say, . So if they're all the same, what letter should I use? I'm going to just use a question mark, okay? So they're all the same times whatever the question mark is should be 1. So the question mark should be 1 over n. And then I explain that we can write them as H, 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 T. It feels weird though, because I said these are quantitative. This is a quantitative variable. The outcome should be, the values it takes should be quantitative, but I can convert them. I can convert all of them to a number if that makes it easier. Like I could assign H as 0 and T as 1, and this would be all zeros, or in other words, 0. And this one would be a bunch of zeros in front and then 1. So you can see I can make numbers out of these. It's just it's acting like a label in a way, like you say, it's like a categorical, but we actually made numbers out of them. And are the numbers meaningful? I guess if you define them as sorry, if you it'll make more sense actually, because it does look more categorical here. It'll make more sense in the next example how I make it quantitative.
I have a question.
Yeah.
Why are there 4 attempts? And
Oh,
then
we just defined it.
okay.
Yeah, that is given. Okay. So I'm gonna make this a little clearer. Let's define X instead of just the outcomes that we've illustrated here. Let's define X as the number of tails and 4 flips of a coin. So now I'm going to group my outcomes together, and I have a new variable. So this one looks like 0 tails. This one are all the ways I can see 1 tail, all the ways I can see 2 tails, all the way I can see 3 tails, and all the way I can see 4 tails. And I'm going to do the same thing as above. What is the probability distribution? So I called the probability distribution here just each outcome is 1/16. And I didn't do anything more. I didn't make a table or do anything like that there. But we could make a table here. And again, sort of analogous to what we had with the normal distribution, but it's a simpler table.
I have a question. If we transforms the H and T's to zeros and ones, how do we make these categories?
Are you talking about here or here?
If si en lugar, if we don't have the T's, because it's technically, or as I understand right now, it's maybe categorical, but we could transform them to numbers, like as you said, 0 to H and T, it will be 1.
Mm-hmm.
So how do we make like this table with just zeros and ones?
If we were to do that, well, this one was, you see this, if I made these zeros and ones, this would be 1, 10, 100, and 1,000. Anyway, I think you're making it, you're thinking of it more complicated than it is, but basically this has 1 T in it. So whenever there was a 1, you'd put them in here. And this would have 2 T's and you would have, this would be 2 1s would be 2 T's. And this would be 3 1s would be 3 T's, and this would be 4 1s would be 4 T's. So this would be zeros. So I'm dividing it into terms of outcomes. I want to see out of 4 trials, I want to see no T's, 1 T, 2 T's, 3 T's, and 4 T's. In terms of, doesn't really work as a number on a number line though. So that is strange. But I've redefined these. These are the numbers I'm going to use. This is the, this is my new number. This is my discrete variable with 0 through 4. And my probabilities are going to be based on how many of these I see. Each one of these has a 1 in 16 chance. So what is the probability of each one of these outcomes?
So it will be 116, the number of outcomes. So for example, 1T will be 116 plus 116 plus 116 plus
Right.
116.
So this is what I mean, that most people have an intuition for probability that you can just add these together, right? So I know I can just add these probabilities together. And that's because it's either this or this or this or this that makes one that has one tail in it. So you have an intuition that if I say this or that, I can just add the probabilities to find the chance of any of them. So this is what I have here, is I have it all written out here. This is the probability distribution. These are the values. I use small x, just like I did with the normal distribution. I use the small x to indicate the value. And then now I'm going to say probability that the variable takes x. So the capital X represents the variable name. And this represents the value, just like we did when I talked about the normal distribution. And let's see. I guess we already did this up here. So we did this already on the other page. I can write those as decimals too, and I can see that they all sum to 1, right? Because that's the way we constructed it. And then just like the normal distribution, we can use this table to answer questions. So this is what we're going to do for this module 6 and 7 and 8 is, and I guess 9 too. No, yeah, sorry. Yeah, 6 and 7 and 8. We're going to talk about different variables. We want to know the probability distribution, and we want to use the probability distribution to make predictions. So this tells us that the chance of getting, given this distribution, that what's the chance of getting no tails? It's 1 in 16. What's the chance of getting 3 tails? It's 4 in 16. What about at least 2 tails? So that's how I would say it in words. How would I write it in symbols? So I'm going to write here, because it's discrete, I can list all the possible outcomes for X. So I list them here, 0, 1, 2, 3, 4, and I identify in this question, at least 2 tails means, and again, like I told you last week, when you have problems understanding numbers that you're staring at, think about it in dollars. So at least $2, right? At least $2. Well, that means $2, $3, or $4. So then you go back to the distribution, 2, 3, 4, and you just add those up to get the answer. You can write in words like that, but in symbols like this. Notice, so we're going to talk about this in a minute about the symbols, because everything looks familiar, but what's different is essentially the distribution. So I can take 2, 3, and 4 and sum them. If you don't like fractions, you don't have to use the fractions. It's just easier to add them as fractions in this case. So I'm going to leave them as fractions. So that's 16. 11, 16. Questions about this so far? So I created a probability distribution. Those are the possible outcomes. And then I can look at what I call compound events, you know, combining those simple outcomes into events. So different from the continuous distribution of the normal distribution, the equal sign matters. Okay, the equal sign. Now, in fact, you can't even write this when you talk about the normal distribution, right? I mean, the answer will always be 0, right? If there's an equal sign, but suddenly I'm like using it. Well, because it's discrete, there's 5 possible outcomes and it takes on the value. It's different than continuous where it can take on any value in between. So solve the rest. Give you a minute to do the other 2. You have your other class today at 12, right?
Yeah.
Yeah.
Yes.
Do we leave the results as fractions or do we?
Yeah, you can leave it as fractions in this case. Yeah. And in general, you're going to have multiple choice problems to choose from, right, for your test. And you're going to see if I want the fraction or the decimal. So you should be able to manipulate both. In this case, it's easier just to stay with the fraction. All right, so let's finish this then. So x less than 3. Less than 3 is 0, 1, or 2, not including 3. And so I write down 116, 416, and 616. I get the same thing. So you notice there's symmetry, okay? This is going to come up later when we get to talking about the binomial distribution. But there's a symmetry here. It's a pattern. And as I go, you know, these numbers are the same on this side as that side. And again, the equal sign matters. I'm not going to include it because I don't want to include 3. And then less than 1 tail and more than 3 are the extremes, 0 and 4.
Yeah.
So that is a discrete distribution. We've practiced we learn about adding probabilities, because we're saying, essentially we're saying 0 or 4 for this one. For this one, we're saying 0 or 1 or 2, and we're just adding them up. Again, we're using the or. Possibility. Then I have some terminology just to help you read through the notes. And after that exposition, I go through the rules of probability. So are you ready? We're just going to quickly go through the rules that most of them you have intuition for. As I said, all probabilities are between 0 and 1. I put some, I illustrate using a few concepts, right? So S represents the sample space consisting of all outcomes, and compound events A and B consist of combinations of outcomes. And we can get the first 4 rules of probability using these symbols, okay? So I just use A and B as combinations of the simple outcomes of the sample space. Then any probability, A or B, its probability will be between 0 and 1.
May I say something?
Yeah.
I don't know, let me see, what is this? The overview where you have the 4 types of probabilities.
Yeah, I'll get there.
Okay, because I understood it better with this one.
Yeah, I'm just going through this because I want everyone should watch that video. I don't necessarily want to do that whole thing again. I just want to get to the exercise. But I'm just going through the rules. Yeah, of course, that overview is a summary of everything. Okay, so all outcomes sum to 1. I just write it like that. All the outcomes of the sample space sum to 1. That's rule number 2. And rule number 3 is the complementary rule. And it's that 2 events are complementary if only one of them can occur. So in other words, if I know the possibility of outcome A, then I must automatically know the possibility of outcome B. I mean, or in this case, AC, not A. The little c represents the opposite event if there's only 2 complementary events. And I can calculate it as 1 minus. So this should feel also like the normal distribution. If we wanted the left side and we have information on the right side, we use 1 minus. So the symbol AC is the same as not A or A bar. And then you should read through this. What am I talking about? So we've already gotten through 3 rules. There's only 2 more. And those 3 are very intuitive. You already knew that, right? We knew that. We had an intuition for that already. The 4th rule is known as the addition rule for disjoint events. So this is an image of 2 events, A and B, and they do not fill the space. So this is different from complementary. A and B are not complementary because they don't fill the space. So you have A, B, and you have this outside part. What should we call the outside part?
The sample space, not A and
No,
B.
the sample space
Not
is
A and
all
B.
of them.
See, not A and B.
Right. So being outside here You can call it, so this, I use the example of going to a salon. And you can get one product or one service like hair color, and you can get another service like a manicure. And if that's what you're focused on, you would know the probability of A and you know the probability of B. And in this example, people going to this salon, if these are the only two possibilities, can only have one service. They can't have both. It's either they have the one service of hair color and the other service of manicure, but they can't have both in this diagram, or this, Venn diagram, it's called. Out here are the other services that I'm not focused on, but there's other services that exist. So this is something else out here. And I'm not labeling them, I'm not interested in them, but there are other services. And I don't know about them, I don't have information, but they exist and they could be consumed or purchased together, but these two cannot. Okay, so we give a name to this outside space in general, and we call this space not A or B. That's all I know about it, because I haven't defined anything else. So here's an example. A is the event that a doctor is in his office at 9:30. B is the event that he's in the hospital at 9:30. His office is not the hospital, so they're separated. And then I'll just call it other events in general. And then I ask you to answer a few questions here. How many people did this already?
I did.
Okay, so
Me
I don't want to
too.
be too
Me
repetitive.
too.
Who
Me
did
too.
Who didn't do it? Put it in the chat so I know if I'm wasting people's time review.
I didn't do it.
Okay, Christina. It's okay because you did the overview. That's the most, overview is like a summary. This is just going through it in like talking about the rules. Okay, so there's a few people who didn't. Okay, so try this. Try this exercise. I'll give you a few minutes. So when I start the video, the instruction is about the overview, which I start with the overview so everyone sees the end result of the big picture result. But I still need to talk about the rules. Okay, how'd it go?
Do we,
So, uh-huh.
do we put the answers in the chat then?
Yeah, you can put the, okay, so let's do A. So what'd you get for A?
Oh my god.
So probability, oops. Probability of not in the hospital. Hospital was B, right?
Yes.
Yes.
So not B is 1 minus chance of not A, of chance of B. And so that's 1 minus 0.27, so it's 0.73. Any questions? So the probability that he's either in his office or in the hospital, so that's A or B. And we learned about, or we have an intuition for or, we just add them, right? So we're finding out if he's in A or B, so 0.48 plus 0.27 is 0.75. And now we're going to define the outside, not in the hospital or in his office. We're going to define the whole outside as he's home. Those are the only other event possible. So we write that as not A or B, because we want to find the outside part. You can write it as 1 minus probability A or B. And I know what that is. So the answer is 0.25. Okay.
I do explain A, I got B and C, but A,
Because
which
the,
would probably be easier
hospital,
to.
the hospital is B, so it's this one.
Because it said not.
And it's not. Right. Exactly. So we're able, so this is you're practicing the or, that you can just add these to find out about this or that. Also, you're practicing the complementary rule because you're saying not A or B. So we practice both rules 3 and 4.
Permiso, profesora.
Ajá.
¿La probabilidad no se representaría en porcentaje o se puede dejar en decimal?
No importa.
No
Decimal
importa.
or done. It can be either way.
Ok.
And we can imagine these numbers, like the 48 and 27%, were derived by looking at the doctor over a long period of time to see where he goes. And we see the long run relative frequency of his behavior and come up with these probabilities. All right, so I make in the video presentation, I do this whole thing. I want you to watch the entire video. And so we already talked about complementary events, disjoint events, and I ask you to calculate the probability of A and B, the probability of A or B, and the probability of not A or B for each one. So this is the first time I mentioned A and B. What does A and B refer to?
They're overlapping.
Where they intersect, where you can have both of them happening at the same time. So we haven't talked about that yet. We
Never.
talked about, right, in this case, it's never, right? Here it's never either, but then there's some examples where I talk about it. So I'm going to go through these and then I'm going to refer, because I go slowly in the video. So let's just go through these. So if you say never, never translates into 0 probability for that one. What about A or B for this one?
100 always.
Right, exactly. It's always 100% or 1 for complementary events. I don't even need to know the numbers. I don't even need to know the probabilities. I already know it's 1 because complementary events fill the space. And what about not A or B?
0, neither.
Right,
No.
never. So if events are complementary, you already know the answer for all 3 of those possibilities.
Professor, in that case, it's 0 because both events fill the sample space, right?
Exactly.
Thank
Yeah.
you.
So there's nothing else possible. I could go through the trouble and write it like I did last time, 1 minus probability A or B, but then this one is 1, and that's 0. Or just realize there's nothing else. There's no other event. All right, so let's review this one. Disjoint events. So in this one, I actually need some numbers, right? To be able to calculate some things here. So if I tell you, given the probability of A is 30% and the probability of B is 40%, you can calculate each of those. So I give you those. That's given. You can't really see it in the graph. It's just this is a Venn diagram, and it's used to just show you, the concept of events, but you shouldn't go by scale and say, oh, this one looks bigger than that one or anything like that. Okay. So A and B refers to where they intersect, where they happen together. In disjoint events, they never intersect. So there's no possibility. It's like I was mentioning about the doctor, right? He could not be in the office and the hospital at the same time. What about A or B? What do I do?
Add.
I can add. I can just add because, in fact, that's what we've been learning so far. I can just add them. There's no problem in just adding events when it's or. So it's going to be 0.7. And what about not? Not is always 1 minus A or B, or whatever is in there in the not. And I already know that is 0.7. So this is 0.3. So those are good. We're covered. And notice that complementary events are disjoint, but disjoint events are not complementary. It doesn't have these properties, okay, if they're disjoint. I actually have to know the values to calculate or and not A or B. But complementary events are very specific. They fill the space.
Can you repeat? So complementary events are disjoints, but
Disjoint
The
events
second
are
example.
not complementary. Because they don't fill the space. Okay, so now try the third one.
In this one, you give us into the overlap value.
So right now I didn't give it yet. I want to talk about that. So can you do any of these with the information I've given?
No. You need to know the overlapping space, right? To be able to do it.
You need to know the overlapping space to be able to do it. You can't just, with the information I provided, you don't know what the overlap is. Some people might think they know, but they don't know. All right, just calling this A and B are overlapping and seeing this image, I won't be able to do this unless I'm given information. It's let's say it's 10% given, all given. I can't calculate it from the picture. I know it from my research, let's say, from my observation and recording of long run relative frequency. This overlapping part is called A and B. First time I mentioned. So I take it from my givens that this is 10%. Okay, so A or B is what?
60% of 0.6.
So if I just add these, that's not correct, because if I take A, but it coincides with B, and then I add B, I've double counted the coincidence, this portion. So I have to add them together and take and remove the overlapping piece to get the right answer. So it's 30, 40, and then minus 10 is 60. So you're right. Questions so far? So this is actually another rule. What do I call it? Is it 5 or 6? I think it's 6. There's 6 rules. So I'm going to show you rule number 6 first, but this is the addition rule for overlapping events. Okay, when they overlap, you have to remove the coincident piece or the part. And so now to find the outside, we just have to subtract the 0.6 to get the 40%. Okay, any questions about that? So that's when you have overlapping events. So as I explained before, if you go to the salon and you have hair coloring done and a manicure, obviously this is very gender specific, right? Well, I know men get manicures too, it's true. But I use this example because I used to teach nurses and they were mostly women in there. So I had to try and make something relevant for them. So this is my example. And then in this salon, you can actually get both services. And we figured out over long run observation that 10% of clients get both services, hair color and manicure. And then there's all the other services out here that we're not so focused on, but they're out there. And the chance of someone having them is 40%. Notice that if they have those services, they're not having A and B because they don't cross over. Keep that in mind. They're different services, not A or B. And now the punchline, or now where I really want to make my point, because all of this was pretty straightforward. Maybe you learned something there, but you pretty much have an intuition for all of this. But now I introduce the idea of independent events. And it's a very specific term in terms of statistics and probabilities. Independent events are overlapping. They're not disjoint events. They're not complementary events. Well, they could be. Yeah, they have to be overlapping. Okay, so it's different. It's like a fourth. I have only one more diagram relating to events that I have later in the notes, but independent events look like overlapping events, but it's very specific. For those people who looked ahead or read ahead or saw my videos, what are independent events? How do you define independent events?
I think it was that the outcome of one does not define the outcome of the other one.
Okay, close. So knowing the outcome of one does not change the probability or the distribution of the outcome of the other. So when you're flipping coins sequentially, if you see a head, you don't know anything more about the next outcome, just that it's 50% chance to see another head. Doesn't change anything. That's independent events.
So it can be complementary too, or? and
They
then
are,
they-
they are not complementary because of the very definition that I said they have to be overlapping, and complementary events are not overlapping, so they cannot be. That was Christina, right?
Yes,
Okay, that makes sense? Because they have to be overlapping, and overlapping, complementary are not overlapping, so they cannot be complementary.
Right.
Okay. So it looks like they're overlapping, but they overlap in a very specific way. And I'm just going to say it here and you guys can see my explanation. When So when events are independent, we know what the overlapping piece is. It's just the multiplication of the two events. And the reason for that comes from the conditional, understanding the conditional probability. So I'll explain it like that first. So in general, this is how we define, or this is how we would find the probability of two events happening simultaneously. We would take the probability of the first one and multiply it by the probability. So we're saying A happens. So that's the chance that A happens. And of the times that A happens, a fraction of them also have B happening. That's what this is. So out of the A times, B happens. And you multiply those because I say the word of. So out of the times that A happens, B also happens. So I multiply because it's of. Por. So that is really how you find the probability of A and B. You could also find it this way. There's no reason why you can't find it this way. I can go with B first. So probability of B times the chance that I see A given B happens. So this is called given. So multiplying those two together gives me the probability of A and B. That's how I can calculate that. I didn't do it before because I just gave it to you, right? I gave you A and B. But in fact, I would need to know either these two or these two probabilities to find A and B. If A and B are independent, however, then the chance that B happens given A happens doesn't change. It's still B. There's not a new number or a new probability. It's the same thing because the event A does not, seeing the event A occur doesn't change the probability of B. It's not a different number. It doesn't change, doesn't become 10% or less. So when would it become different? So let's say I'm going to the salon And I said A was hair color and B is a manicure. So imagine a female client has her hair colored. The chance that she's also going to get her nails done or her mani pedi probably changes because hair coloring is very expensive, right? So it might not stay the same. It might go down. So these might be different. But if I tell you, at this salon, it doesn't matter. Price doesn't matter. People have money. If they're gonna get their nails done, it doesn't. Sorry, if they're gonna get their hair done, it doesn't change the chance that they're gonna get their manicure done. Doesn't change anything. No impact. So those would be independent in that case. Also, if they're independent, probability of A given B, so, getting a manicure, it doesn't change the chance of getting the hair color. So because of that, what I wrote above changes. This becomes, let me clean this up. So this becomes probability of A times probability of B. Or probability of B times probability of A. Questions? So independence is a very specific occurrence, and I've described it. However, in statistics, it makes the mathematics very easy. Okay, it simplifies the mathematics, and a lot of statistic sampling theory, it depends on independence. And that's what we're going to focus on. But in general, independence is not a given. I just described, I gave you an example where it's not a given. And I do very many exercises to talk about checking for independence that you can practice. All right, so let's finish off with getting these, and then we still have time. So we want to get the probability of A and B, A or B, and not A or B. So A and B would be? That's right, 0.12. I'm just multiplying them together because I was told they're independent. A or B would be the same as I did up here, but I'm going to change it from 10% to 12%.
So it's 0.58.
Yeah. And not A or B?
0.42.
All right, so things change. I'll give you a chance to think that over. So some of the things that were new here maybe was this one. This idea of what is really, oh dear, hold on. What really is, A and B. Okay, that's sort of new. And then understanding independent events through that. Okay, so I wanted to talk about that. You can review that watching my explanation of this that goes through the whole thing. I spend some time talking about that some more. I give this example to consider the long run relative frequency in the manicure. Oh, okay, I made A manicure and B hair color. Anyway, using the long run relative frequency concept that let's say you have 10,000 women going into salon, an independent case, this is actually case 4. Like in the 4th drawing, if you're told A and B are independent, how many women? I can translate probabilities into women, and maybe that helps people understand better. So we know that out of the 10,000, 30%, so we say 10,000 is enough to see long run relative frequency. So we can make this estimate, okay? So 3,000 women will have a manicure. Because of independence, then out of those 3,000, a fraction of them will also have their hair colored. So I can just multiply to find out what that is. That's why I'm able to multiply when events are independent, because the subset of women that have had a manicure who have their hair colored at the same time doesn't change. Okay, so I get to still use this 40%, even though I've gone to a subset of women, which again is not necessarily the case because they've already spent money. They don't want to get their hair done as well. It's going to be less. But if they're independent, then you just multiply by 40% and you see 1,200 women. And I can do it the alternate way as well. So spend some time, look at that, convince yourself of the case. Always differentiate between what I give you, work with what I give you. And what is just known. Okay, so this is the 5th drawing. This is the 5th drawing. And I use the example of the ways that you can see 4 flips of a coin and the variable number of tails. And I ask you to depict A, which is observing 2 tails and 4 flips that look like this, and B, observing less than 3 tails and 4 flips that look like any of these. Draw event A and event B in this sample space, and then answer the same questions we just answered. Probability A, or I guess I started with and B, probability A or B, and not, probability not A or B. So how many people, I guess I don't know, most of you, half of you didn't do this, so try that. All right, so ready? Yeah, I hope you all understand from whatever angle what I'm trying to demonstrate here. So you can see that inside of event B, you find A. So it means that if I want to depict these, I know it doesn't fill the whole space because there's B has half of the events possible. So B is like this. And because A is inside of B, I actually draw A inside of B. It's not overlapping. It's contained. And any questions about that? So that's why it's a fifth drawing. It's different from the others. In relationship to two events, not overlapping, it's contained inside. So when I think about A and B, that's both of them at the same time. Where is that happening? Well, this is B and this is A. And so any of these would be overlapping or would be touching both A and B. So it's only that. So this is just equal to A's probability, which we know is 616 or 375. In terms of A or B, either here or here, all the possibilities are basically captured in B. So that's going to be B, which is 1116. Or the decimal 0.6875 or 68.75%. And then the not is everything else. So it's just basically, well, 1 minus A or B, but I know A or B is just B. So it's 516. It's easier to do that fraction representation. Okay, so once you understand their relationship, it's easy to solve. Any questions about that? So outside here are all the other events. What's missing is 3 tails and 4 tails are out here. Okay, so I'm going to say with that, work through these exercises. These are explained in the video. I do a video about all of this because this comes up again. There's a pre-edited, what am I going to call it? Like the older videos that I did just on the pages there's that. Anytime that I write this, it means there's a video just on this that you'll find. And so look at all of that. Then I arrive here, and what I talk about here is I actually use this material here for module 7. Okay, so module 7 is just going again back into module 6, but focusing on the different probability models, the discrete distributions, the continuous distributions. And so that's what you're going to do next week. So you're going to continue here. But where I want to start is, so these few pages here are actually, and then the practice exercises I give for module 7. So if you've done all of this, you've already done 6 and 7. So look at all that, and I wanted to go here. This is where I wanted to go. The balls in the box problem. So this is the review at the end. It's on it's on page 21. How many of you did this? You can brag a little bit. Put it in the chat if you did it already. I think this is a fantastic exercise that goes beyond the overview, but reviews everything. No one did this? Catalina, good. I'm sorry, Catalina, we're going to do it again. I hope it helps. All right. That's okay? Good. Okay, so not many people are bragging that they did it. Okay, so then let's do this. So consider the following two boxes containing balls with numbers. You will randomly select a numbered ball from the first box and then randomly select another numbered ball from the second box. Demonstrate the outcome of interest, which is the set of numbers on the two balls that are chosen from the two boxes. What is your sample space? So try that. I give you a few minutes. Let's take 5 minutes to do that and take a little break, okay? So let's see you back here at 11. Okay, I'm back. Oh, I should have turned off the recording. Oh well. Okay, so did you do it? All possible outcomes. So what we can do is say box 1. We have 1, 2, 3, 4, 5, and box 2, 1, 2, 3, 4, and all the combinations possible are 1, 1, 1, 2, 1, 3, 1, 4, 2, 1. Always the
So, Professor,
first. Yeah.
so I multiply 5 per 4, and that's the total amounts that the max combinations I can do.
That's right. Exactly. Exactly.
Okay.
Was that Brenda? Or Christina?
No, Vanessa.
Vanessa, okay. 2, 4. 1, 3, 2, 3, 3, 3, 4, 1. And you see I'm getting 20, right? So those are all the possible combinations. And the order is already determined because I have to pick from box 1 first. So 20 possible outcomes. All equally likely. So each one has a probability of that's A. That answer is A. That's the sample space. Now you could write it like that, or you could, I think in the answers, it shows like 1, 1. It does it like this or something. 1, 2.
So in terms of answer like test or sorry, exam answers, can we just put 4 plus 5? The result is 20 possible outcomes, and that's
Yeah,
it.
you gotta show me. I don't know if you know what they are. You have to show me. So
Right.
the
So-
table, or you know,
So we need to do the table basically.
yeah, like I'm cheating here, but you have to write them all in. That would be your sample space. You have to depict them. You have to show them what they are.
Okay.
Okay, how many people got that or knew what to do?
Professor,
Christina?
does it
Wait,
matter if we
it's
put,
Christina, so I keep thinking it's her. Sorry, who's speaking?
it's
know.
Carolina.
Carolina, dime.
Does it matter if I put box 1 on the side or at the top, and if, like, does the order matter? I mean, I will get the same results, but I don't know if
Yeah, it's
the
okay.
format matters.
It's okay. It's okay, but This is the most intuitive way to do it.
Okay.
Yeah, it's okay. If you put box 2 first, it's okay. It's just that you have to be clear that the first one is box 2 and the next one is box 1. You have to say that somewhere. This explains to me what's been done.
Okay, thank you.
Okay, so how many of you got this or knew how to do this? You can brag in the chat. We're going to try part B. Let X, now we define a variable, not just the outcome, because this is the outcome of 2 boxes, the balls. But now we're going to define X as the sum of the numbers on the 2 balls selected. But now find the probability of X. So we're going to take this and I'm going to replace. So let me store this somewhere so I don't delete it, but. Okay, so let's replace each cell with the sum. So I'm using this as my chalkboard. This is 3, right? So you get the idea. This is going to be 4, 5. And basically I know what to do for the rest. Rather than putting them side by side, I'm putting the sum. Sum of the numbers on the balls. So this is 3, 4, 5, 6, 7, 8, 9, 10, 5, 6, 7, 8, 6, 7, 8, 9. So you see some numbers repeat. So what we're going to do is, like before, we're going to define the variable. We're going to present the probability distribution of the variable with the values here and the probabilities down here. So what are the possible outcomes for the sum of the numbers on the balls? Two is possible, 3 is possible, 4 is possible, 5 is possible, 6, 7, 8, and 9.
Is I think-
Professor, the sum in the line 3 is right?
I don't know what I did there.
Okay.
I don't know. I think I fell asleep.
I was confused.
I'm sorry, I fell asleep talking. I kept counting. Sorry about that.
Okay.
That's so weird. I kept counting. I must have been thinking of something else. So 4, 5, 6. Sorry. There. I did the rest. So weird because I did the rest correctly. My brain space was compromised. So there's 20 possible outcomes. But now, or there was for the last exercise, but now there are only 1, 2, 3, 4, 5, 6, 7, 8. So some of them are more likely, correct? So we need to calculate every cell had a 1 in 20 chance, but now 2 of them can be 3, 3 of them can be 4, 4 of them can be 5. So how does that change things? So the chance of a 2 is 1 out of 20. What's the chance of 3?
2 out of
2 out of 20.
Exactly. And then chance of 4.
3 out of 20.
3,
5,
4 out of 20.
4.
6,
4,
4 out of 20.
7,
3,
3 out of
8,
2.
20. 2.
and then 1 for 9. And that should be 20 out of 20 or 1. So that is the distribution for the X, the sum of the numbers on the balls.
That is symmetric.
And it's symmetric. Yep. Good observation. Hope you can still see all that. Okay. Are we ready for C? So this was A. This was A. This is B. Now C. Define the following events. A, the ball drawn from the first box has an even number. B, the sum is odd. And C, the sum is 9. So I want you to find the probability of those events, compound events. If you guys are watching on your phone, I think it's gonna be hard to see this. I have a big screen. So let me take the C part question onto another page. Okay. So how would I find A?
You get it for the first table when you have the combinations. Not that one, the first one.
Well, this one gives me the same, right? Because it's the ball drawn from the first box is an even number. So I can take
Well, yeah.
this because I'm using yeah, I'm going to use let me go back and make sure. Yeah, because I'm going to use X. It's not clear here, I guess, but yeah. So I'm going to use the the ball drawn from the first box as an even number. So that's going to be red. What's the probability of A?
50%.
8 out of 20.
8 out of
20.
20.
20.
Yes, not 50% exactly because it's not half of them. It's a fraction though. So
Okay,
probability of
got
A is 8 out of 20 possibilities. We'll leave it as 8 out of 20. No, we can simplify a little bit. 4 out of 10. No, that's still, what am I doing? It's 2 out of 5. One out of 5. Is that right? No, it's 2 out of 5. 2 out of 5. Yeah. Okay, let's do B. We'll do B in what color? I'll do it in green. Or blue. Let's do blue. The sum is odd. Oh no, I already have blue. I got to do a different color. So green. The sum is odd.
3 out of 5.
The green.
10 out of 20.
10, yeah,
It's
10 out
half.
of 20.
Yeah. Okay. And the last one, C.
It's 1.
1 out of 20.
Okay. All right. You can see it. Probably should have erased the blue in there, but all right, so now let's do part D. Oh wait, did we finish C? Yes. So part D. Find A and B, find A and C, find B and C, and determine whether each pair is of events is disjoint, independent, or neither. All right, so this brings together everything we've done so far. Let's look at A and B. Do the red and the green overlap?
Yes.
Okay, let's mark in yellow. I know I have too many colors, but we're going to continue what we've done. So I'm going to mark in, well, maybe purple. Is purple different enough? Purple or fuchsia. Okay, we'll do magenta. I don't know if that's magenta or fuchsia. So let's mark where A and B overlap. So red and green here. Red and green here. Red and green here, and red and green here. That's it. So what's the probability of A and B?
4 out of
Out of
20.
20.
4 out of 20. Let me put it on the other side.
I didn't follow, Professor. Can you repeat, please?
Okay, where A and B overlap, A is the red and B is green. So A crosses with B here. And A crosses with green here. So in other words, everywhere that the ball of the first box is even and the sum is odd. That's what we're getting. Both of those at the same time.
So in that case, you don't need to put the numbers that are crossed, just the amounts of the numbers, right? Like the
Those are the
amount, like
events.
4
those are the-
times.
yeah, like if I was to, okay, so here I presented the probability that was, I was asked for that, but if they asked, show me the event A and B,
Mhm. Mhm.
right?
Yep.
Or I can make a sample space for A and B. Okay, so now let's answer, before we go to the next one, let's answer the question. Are A and B disjoint, independent, or neither? So A and B overlap, we already got that. So either they're independent or not independent, because they do overlap, they're not disjoint. Right? So the question is, the event A and B, so sorry, are the events A and B independent? How are we going to figure it out?
I think no. I don't think they're independent. But I don't know how to put it into words. I don't know if I'm right.
Okay. Okay, so who, okay, if you think it's independent, put independent in the chat. If you think it's not, just put not independent in the chat.
Would 2 and, wait. 1,
Was there a question? Sorry.
well, I didn't finish. What I was
Okay.
I'll ask it later.
So I do the same thing, just 3, 4, 5, 6, 4, 5, 6, 7. I shouldn't have circled the 2s here. That might be confusing. 2 is not an option. I get carried away. So A was the ball drawn from the first box is even, and B was green, some is odd. So this is what we're staring at. Okay. All right, let's see. Okay, okay. All right, so let's do this visually first, and then we'll do it mathematically, and then I'm gonna let you go. You guys will finish the rest. The rest is easy. So look at red. Inside of red would be the subset of A. Right? So probability. And green was 10 out of 20 or half. The green was B. Notice that the purple, which is the A and B, we said it was 4 out of 20.
Is it 4 out of 20, Professor, or 8 out of 20? Probability of A.
8 out of 20 is 2/5. Sorry. Yeah. 8 out of 20. I don't know what I'm doing. 220. I'm thinking ahead. 2 out of 5. I'm just copying from the other page. This is not new. And then A and B is 4 out of 20. See what 4 out of 20. All right, so A and B is 4 out of 20. A is 8 out of 20 and B is 10 out of 20. Now notice inside of A, what fraction of A is B? So in other words, go inside of A, which is the red, and how much is B? So now you're in the subset, you're just here. So in other words, you're out of 8.
4.
4 of 8.
Yeah, in red, in the subset of A, that's what conditional means. So I'm trying to help you understand conditional. So I'm in A. So A is just the red. And how much of A is B? So it's 4 out of 8, right?
Yes.
In other words, it's 1/2. So why do I care? What does that tell me? Outside in the whole in the sample space, or in the consideration of all the events and outcomes, B is 1/2. Inside of A, B is 1/2. What did we just show? Oh,
That was me, but I don't know how I did that.
that was you?
Yeah, I don't know.
Oh, I'm like, where'd that come from? Okay, can you undo anything? I don't even know how that happens. Anyway, don't worry about the yellow line. That was not me. There, I'm perplexed. I can't even see it on my screen. I guess you're able to edit. There you go.
I did it.
You
Okay.
did it. I don't know. It said undo, or you
I
did
don't
it?
know what I did.
Okay, whatever. Okay, so back to what we were saying. So B in the greater sample space here, B is 1/2. Inside of A, B is 1/2. So we've just demonstrated that it doesn't matter. if the other event happens, it doesn't change the probability of B. So as I explained before, this is equal to the probability of B, so A and B are independent. And I'm going to show you another way to do that. So this was easy because you can visualize this. So being in the subset of A, you only have 8 outcomes and 4 of them are B. So that's where they overlap. But the fact that A happens and the probability of B doesn't change inside of A means that they're independent. That's exactly what independent means. If the other event happens, it doesn't change the probability of your event of interest. So the other way I can show this is to say, sometimes I use the symbol like that for and, but I don't have a habit of doing that, so I didn't write it. So this is my statement, right? If A and B are independent, then A and B is equal to probability of A times probability if A and B are independent. So let's check. We can verify. What is probability of A and B? We found it before. It was 1, 5, right?
Mm-hmm.
And what's the probability of A times the probability of B? Well, we know A is 2/5 and B is 1/2. And what do you get?
2/10.
2/10 or
1/2.
if you guys are not good with fractions, I got to do this one more time, but basically it's the same thing. So since they're the same, it means they're independent.
1/5. Okay.
I can do it all with the other numbers. Just let me do it with without the I can do it without the rounded numbers or the reduced numbers here. I could say probability of A and B is equal to 820, right? And then probability of A times the probability of B is equal to 820 times 1020, which is equal to 1020.
One-fifth.
Yeah, but I'm trying not to reduce it, so
Sorry.
yeah, it's okay, it's okay. A is 820. This is the wrong number here, sorry. It's not, it's 420. I'm trying to be less confusing and I just confused it again. Okay, I'm trying not to do the rounded numbers, just so you remember the picture. So there, A and B was 4 out of 20 total, out of the total, not the subset of A. A was 820. Originally, there were 8 out of all the 20, and B was 10 out of the 20. And so when you reduce this, this is gonna be 420. Because you're gonna cancel here. And then these are gonna cancel here. You can do it all in decimals too, if that helps you. So the answer is going to be 420. Again, either way, you've proven that the probability of A and B is just A times B. So that's how you can prove independence. Check if this holds true. Verify. Sorry, I copied the wrong. Thank you. I like this explanation the best because you can see it. The chance of B happening inside of A is the same as B happening in general. So the probability of B didn't change either in the subset or out. So that's why A and B are independent. And I could also do it the other way around. Inside of B, B are the green. How many are A? So the subset of B is how many outcomes? 10, right? There's 10 green outcomes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And out of those 10, how many are A?
4.
4. Or in other words, 2/5.
Can you say that last part one more time, Professor? About A and B?
B is the green, right? So inside, so how many green possibilities are there? It's 4. Sorry, there's out of B, there's 10. There's 10 possible Bs. Right? The event B captures 10 outcomes. That's the subset B. And inside of B, 4 of them are A. So 4 out of 10 inside of B, this is the conditional being inside of the subset B. And that's 2/5. But A, the chance of A is 2/5. So the chance of A didn't change whether I'm in B or in the general, in general. So that's why A and B are independent. So I could do it either way.
Perfect, thank you.
All right, so you guys can finish that exercise and get through the notes and finish modules 6 and 7, which are basically the same notes. I will post connect exercise that will be due after next class. So you should just basically wrap this up this week, and next week we're going to start with module 8. In the schedule, how did I do it? I think that's what I did. Let me verify the schedule. Yeah. So just finish probability next week. And we'll talk about probability. And if we have time. So next week, I'll talk about the Bayes because I didn't get to the Bayes stuff, but you still have, for next week. We can talk about the Bayes stuff. I can answer your questions. I didn't get to the homework problems, but we can talk about that next week. We can finish probability.
Okay, so next week is still probability.
Exactly. Let me show you on the platform so you feel reassured. It's a nice surprise that we stay with probability. Okay, see here? So yeah, this is all module 6 and 7 are the same documents from 6. We just continue. Okay?
For this week, there will be assignment in Connect or
I
no?
will put it because today is the last Connect one ending, so I'll put one up today and it will be due in like after next class on the
Okay.
Sunday or Monday. We'll see how you're
Perfect.
doing. All right, so catch up with the probability stuff and then I'll answer all your questions about probability next week and we can do some review exercises. And I think we'll be done with probability. I will talk about binomial, so you'll get a little of introduction to binomial, but then you'll have, I gave you 2 weeks for module 8. So it's going to be, you're going to have like 2 weeks now for every module. It means there's more material, but you have 2 weeks. You'll have 2 weeks for that one and then like 3 weeks for the last module. Okay, so this week, continue with the probability material and keep in touch and I'll answer all your questions next week. So collect your questions for me.
Okay.
Okay, thank you.
Okay.
Thank you.
Buen fin de
Thank you.
Thank
semana.
you.
Igual.
Keep your pace. Don't slow down.
Have
Keep
a
the
nice
pace
day.
going. Okay, bye.
Thank you. Bye.
Thank you. Have an excellent weekend.
Thank you so much.
Thank you.